disturbance present in the system. And I'm kind of considering CZ to be the output, and I'm defining like an auxiliary output like this, so that this basically gets rid of all the quadratic terms, the cross terms here. So R is basically like the control cost that is attached with the control. So I'm assuming like really nice problem, well posedness of the problem. So I'm basically taking like C, E to be bounded operators, and as I said earlier, in the input, disturbance, output spaces, and the state space all like Hilbert spaces. And I'm assuming that the disturbance is square integrable, and the H infinity control problem is posed this way. So we call this particular notation gamma as the attenuation limit. So for a given attenuation limit, the problem is, can we come up with a control such that the closed loop transfer function from disturbance to the output, the H infinity norm of that closed loop transfer function should satisfy this criteria. So is there a control that achieves that particular attenuation limit? So that's the question. And I'm just to make things simple, I'm only looking at the state feedback problem here, and I will briefly talk about the output feedback towards the end of the talk. The question is, why use the H infinity norm? So the H infinity norm of the closed loop transfer function. It basically is equivalent to find the L2 gain of the system. So you reduce the H infinity norm of the system, it basically means that you are reducing the effect of the disturbance onto the output of the system. So the solution for the H infinity control problem is well known, and based on these conditions like stabilizability and detectability assumptions, we have that the closed loop transfer function achieves the gamma attenuation, provided like that statement is basically equivalent to solving a Riccati equation of this format. So I call it H infinity algebraic Riccati equation. Notice that you would have without this term you would have probably seen this in the LP control format. Right? With the disturbance coming into the picture, you have this additional term. So it's very similar to the usual ARE, but except for this middle term. So the problem of solving the H infinity control problem boils down to basically solving this Riccati equation. However, it's not that easy because here all these operators are infinite dimensional. And the good part about this is, along with this, when you solve the Riccati equation, the control is often given by a state feedback, which basically depends on the Riccati equation. So what do we achieve because of the state feedback? Well, now we have basically identified a control that will give you the effect of disturbance on the output, basically just by a factor of gamma, right? So the real question is, can we minimize this factor any further? And it turns out there is a well-identified problem in the literature, which is known by the name optimal H infinity control problem. So that is basically to find the infimum of this particular factor over all possible state feedbacks. So I call the gamma hat to be the optimal disturbance attenuation. So now comes my actual problem. So the way I see it is, I have like a set of finite set of actuators, so that lies on some sort of a compact set. So the idea is, if you look at a 2D plate, so this R cube here is basically like the R2, and omega is basically the plate, the dimensions of the plate. And I have some finite set of actuators placed on that plate. So the question is before getting into that, the way I see this problem is, I'm parameterizing the input operator with R. So R basically at any instant it gives you a set of actuator locations. So we can say that at each particular location of the actuator there is an optimal H infinity control problem to solve. However, it is posed on the infinite dimensional Hilbert space. And I am assuming that the objective function for my problem is the optimal disturbance attenuation at that particular location. So the optimal actuator location, it basically is finding this infimum of this particular location over all possible locations in the place. So the real question is, what guarantees the existence of optimal actuator location? So there is one way I think about it. So I need to first theoretically establish the continuity of this objective function, right, with respect to the position. So the reason is, well, I have assumed that the set that I'm dealing with is compact, and if the function is continuous, then the basic theorem from calculus, it says that you have a minimal cost for that particular function if the function is continuous and you have a nice compact set. So here I am trying to prove that the continuity of this of optimal disturbance attenuation. So I require some set of assumptions. So the first and foremost assumption that I require is this. So the way the actuator location comes into the problem, that's through this input operator. So I require that the input operator be continuous in the norm. So these are like standard assumptions that make the problem well posed, stabilizability and detectability of the system. And also, this assumption is very important for my problem. So that is basically the input operator and the disturbance operator should be a compact operator. So with the help of these assumptions, I was able to show that the optimal disturbance attenuation converges locally around a particular point, rather more like continuity locally.
Does this stabilizability depend on R?
Yes, so that's the basic assumption that I have, that stabilizability at all particular locations, the problem should be stabilized. So notice that this particular problem of finding the optimal attenuation at each location is a problem that's posed on the Hilbert space. So how am I going to solve that problem? Well, approximations are inevitable. So I consider a sequence of optimal efficiency control problems, and each of the sequence is basically based on the approximation. And then I have that for each particular location, I have this particular quantity which denotes the optimal attenuation for the approximating problem. So what for a fixed actuator location, what guarantees the convergence of this cost to the actual cost of the exact problem? And it turns out there are technical assumptions which are required, and in 1988, Icon models, they came up with the conditions that are required for the convergence of the optimal attenuation for fixed actuator location. So I'm now going to put together this assumption and the continuity assumption that we saw in the previous slide, and because of that, I was able to show that if there exists an R hat, an optimal actuator location for the original problem, then along with a particular optimal cost, again this is for the original problem, then you can also redefine similar quantities. These are basically the quantities on the approximated problem. So based on these assumptions, I was able to show that the cost of the approximated problem converges to the original problem, and so does there is a sequence of optimal actuator locations for the approximated problem that actually converges to the original problem. Proof was basically based on the LQ optimal actuator location, which was shown in one of the recent articles by customers. So here is a quick numerical example that basically illustrates my theoretical results. So I am considering the 1D beam problem. So the beam is supported at both the ends, and so notice that I now replace the point actuator. Like point actuator is usually like an unbounded operator. So for all physical purposes, I basically assume that it has a constant effect of 1 over delta over this width of delta. So what's going on here is the observation operator I took as an identity operator. This is basically like you want weights on equal weights on all states of the system, and I've assumed that the disturbance is also an identity operator. So